Welcome back. So, in this lectures we are dealing with 2 degrees of freedom system. In the 2 degrees of freedom system we started with the generalized systems. From the generalized systems we saw how to distinguish between the single degree of freedom system, how to make the generalized system into a single degree of freedom system, how to change them into a 2 degrees of freedom systems or a higher degrees of freedom system. Okay. We set out the rules in order to calculate the number of degrees of freedom of a system. Basically what we told was we have to look into the masses, number of masses and the number of independent motion that those particular masses can achieve. Okay. And the multiplication of the number of masses and the number of independent degrees of motion of each mass will determine the total number of degrees of the freedom system. After that we took 2 examples. In the first example we had a uniformly distributed mass and stiffness system, and in the second case we have a non-uniform distribution of the mass and stiffness distribution. From there we evaluated the frequencies for both the cases, we evaluated the mode shape for both the cases. In the first case what we saw was if the mass distribution is uniform, the mode shape will correspond to the generalized deflection shape for a uniform beam. If the mass and stiffness distribution are not uniform, then there will be a slight deviation from the generalized shape, but again the shape in totality will follow the same pattern. After that we evaluated the frequencies and the mode shape for the first mode and the second mode. Since it was a 2 degree of freedom system, so there will be 2 frequencies and correspondingly 2 mode shapes. So we evaluated them for the uniform case, the distribution of the, when the distribution of the mass and the stiffness was same, it was following the generalized vibration pattern of a uniform beam. For the non-uniform system it was deviating a bit, but in all the general solution was the same. After that we evaluated the response of the 2 degrees of freedom system. We calculated the values of the displacement at the chosen degrees of freedom, and we saw that the total displacement at any given degrees of freedom will be the summation of the contribution from the individual modes multiplied by an amplitude component. Okay. The values will depend upon the initial conditions as well as it will depend upon the frequencies of the system. Okay. So we established this thing, and after that we set up one more problem in which we again saw that we had been given a 2 degrees of freedom system. We established that it is a 2 degrees of freedom system. There is no forcing function in the system. So this is the case of free vibration and the damping in the system is 0. So this is a case of a free vibration undamped system. Okay. So today we will try to solve this system also. Okay. So starting from the last time, continuing from the last time, we have a system in which there are 2 masses and each mass can translate in the vertical direction. Okay. So we have a 2 degree of freedom system. The values of m1 and m2 are given and the values of k1 and k2 are given, and this is the given initial condition for this particular system. Okay. So now we will try to solve this system. Okay. So same as before, our first job is to draw the free body diagram of the system. Okay. So we will try to draw the free body diagram of the system one by one. Okay. So for mass m1, so for mass m1, this is the m1. Okay. So this is the degree of freedom, and it is, since it is moving in the downward direction, so it will have a pseudo acceleration that is given in the upward direction. So since it has moved x1 down, okay, there will be resistance in the upward direction due to this stiffness. So this will be k1 x1. Okay. For the second mass, okay, so this is the second mass, so it has moved x2 down, so the acceleration will be in the other direction. So acceleration will be m2 x2 double dot. Okay. And there is a displacement in the k2. Okay. So what k2 has done? Okay. So since this is moving downward, okay, so since this was moving downward, there will be a resistance due to this k2. Okay. And the net displacement in the k2 will be x1 minus x2. Okay. So, and similarly this K2 will be applied in the other direction, x1 minus x2. Okay. So, this is the total free body diagram of the system. So, from the free body diagram of the system we draw this thing. Okay. Okay. So, from the free body diagram of the system we wrote down the equation of motion of the system. Okay. So, again we will write down the equation of the motion in the matrix form. Okay. And here same as before we see that x1 and x2 both are appearing in both the equations. So, this is a case of a coupled system. Okay. So, this is a case of a coupled system and this is the equation of the motion in the matrix form. Again we assume that the value of x1 and x2, okay, are the value of x1 and x2 are due to the summation of the individual modal contribution. So, it will be a summation of Qn phi n. Okay. So, the contribution from x1 will be due to the first mode plus the second mode. Okay. So, this will be a summation and there will be an amplitude component. Okay. So, again we put the approximation of x1 and x2. Okay. So, same as we did here. Okay. In the last case we assumed x1 and x2 as Qn and phi n. Okay. So, same thing we are doing out here. Okay. And we are putting the values of x1 and x2 in the equation. Okay. So, for a non-trivial solution the determinant of this part should be 0. Okay. So, when the determinant of this part is 0, okay, we try to write down the equation of motion for this particular system. Okay. And we evaluate the frequency of the system. Okay. And after we evaluated the frequency of the system given by this particular equation, we evaluate the values of R1 and R2. Okay. That is the mode shape of the system. Okay. So, this is the value of the first mode, okay, and this is the value of the second mode. Okay. So, here we substitute the values of masses and the stiffness. Okay. So, the value of the first frequency and this is the value of the second frequency. Okay. So, here these are the two mode shapes. Okay. So, this is the value corresponding to the two modes. Okay. So, in the first mode what we are seeing is that the value of x1 and x2. Okay. So, the relative values are, if this thing is going to move 1 unit, okay, this is moving in the other direction negative this unit. It means that for the first case, okay, so since this is the lower value, okay, so this will be the first mode, okay, because this is the lower value and this is the higher value. So, then this will be the second mode, okay, because the lowest value we take this thing as the first mode, okay, and this thing corresponds to the second mode. Okay. So, this becomes the first mode and this becomes the second mode. Okay. So, it means that in the first mode, okay, if the mass 1, okay, if the mass 1 has moved 1 unit to the downwards, okay, the other mass is going to move 1.618 units towards down. Okay. So, if we look this thing as our beam analogy, okay, so here this particular case, okay, can be looked into as a cantilever beam. Okay. This particular thing can be looked into as a cantilever beam case. Okay. So, for a cantilever beam, normally this is my this becomes my first mode. Okay. So, here if the concentrated mass out here is 1 unit, okay, then the values of for the other concentrated mass will be more than this 1 unit. Okay. So, it will be more than 1 unit. Okay. So, here it is coming out to be 1.618. Okay. So, it agrees with our established norm of this particular mode shape, okay, the first mode of a cantilever. So, this one was coming as 1 unit and this is coming out to be 1.618 units. Okay. So, we are in agreement for the first mode. Okay. So, this is the first mode, the lowest mode is considered as the first mode. Okay. So, this becomes my first mode which agrees with my cantilever description. Okay. For again for the second mode, if you look into the second mode of a cantilever, it looks something like this. Okay. So, this is the second mode of a cantilever. So, if mass 1, so it means that if mass 1 is moving 1 unit downwards, the other mass is going to move 0.618 units in the other direction. Okay. So, if you look into the cantilever analogy, okay, if this is going to move 1 unit in this direction, the other one is going to move 0.618 in the other direction. So, this one also agrees with our cantilever beam analogy. It means that this thing, okay, so this lumped mass approximations agrees with our established criteria of the mode shape of the cantilever beams. Okay. So, in this way we can check the validity of our solution, okay, as we compare it back to our established mode shapes. Okay. So, what we have done here till now is that we have calculated the frequencies and we have established the mode shapes for the two frequencies. Okay. So, after that, let us say we have a torsional system. Okay. So, the same analogy we can calculate for a torsional system. Right now, what we were dealing with is a spring based system, okay, where the resistance was due to the inertia effect and due to the lateral springs. Okay. It means that the springs can squeeze and expand. Okay. So, it means that it can have a translational movement like this. Okay. So, right now what we can also do is that we can extend this analogy for the torsional system also. Okay. So, in the torsional system also, instead of the lateral motion, we will have a rotational motion. Okay. So, here if we looked into this particular system, we have a concentrated mass here, we have a concentrated mass out here, okay, and this mass can rotate and this mass can rotate. Okay. So, the rotation of the two masses, so the number of masses, there are two masses and each mass can rotate about its own axis. Okay. So, for each mass there is 1 degree of freedom. So, the total degree of freedom is 2. So, this is a 2 degree of freedom system in which instead of considering the translation motions, now we are considering the rotational motion of the particular system. Okay. And the rotational stiffness is being given by K1, K2 and K3. Okay. Earlier K1, K2, K3 were giving the translation stiffness, now K1, K2, K3 are giving the rotational stiffness. Okay. And earlier there was M1 and M2 which was giving the effect due to the inertia. Okay. Now, there is I1 and I2 which are giving the effect due to the rotational inertia. Okay. So, similarly we can write down the equation in a similar fashion. Okay. So, the equation of the motion for this rotating mass can be written down in a similar fashion, getting the same analogy from the translational springs. Okay. So, now what is happening is that instead of the translational motion, now there is rotational motion. Okay. So, this becomes the two equations of motions for the rotational springs. Okay. And again this is the rearranged equations. Okay. And this can be written in the matrix form. Okay. Now, here we can see we have the same analogy, instead of mass we have the resistance due to the rotational inertia. Okay. So, instead of M1, M2 now we are using I1 and I2. Okay. And earlier we had translational motions x1 and x2. So, now we have rotational movements and the rotational stiffness. Okay. But the formulation is same, again this is a 2 degree of freedom system, the motion is in the rotational form instead of being in the translational form. Now, it has changed back into the rotational forms. Okay. So, here we can see the free body diagram of the system. Okay. So, what we have done is that we have cut out this portion, we have cut out this portion, okay, and we are assuming that the system is rotating this way. So, if the system is rotating this way, there will be an effect of the inertia, the pseudo inertia in the other way. So, it will be given by I1 theta 1 double dot, okay, and due to this rotation theta 1, okay, this spring will engage and it will try to oppose the motion in this direction. The motion is occurring in this direction. So, this is opposing the motion in the other direction. Okay. Again, for this same system, the other part has been cut out here. Now, theta 2 is assumed like this. It means that the rotational inertia will act in the other direction, the pseudo rotational inertia will act in the other direction. So, I 2 theta 2, okay. And due to K 3, okay, in this spring, so the motion is this way. So, there will be a resistance in this fashion, okay. And since this is rotating in theta 1, okay, so there will be a resistance. So, this spring K 2, the rotational spring, will have a net rotation of theta 1 minus theta 2, and it will oppose the motion like this way, okay. So, K 3 theta 1 minus theta 2, okay. So, this is how we can cut it out and form the free body diagram, and from the free body diagram we can write down the equation of motion, okay. From here we can write down the equation of the motion similar to what we have done for the translation masses, okay. So, if this equation is looking funny, we can again see and write it down from here, okay. So, we will write down into our using our D'Alembert's principle, okay. So, for the first case, okay, for the mass I1, okay, the rotational mass I1, we assume that this is going to rotate in theta 1, okay. It means that the pseudo inertial component will act in the other direction. So, the pseudo component is acting in this direction. So, I1 theta 1 double dot, okay. Then the motion is this way, okay. So, the resistance will be in the other direction. So, K 1 theta 1, okay. So, we have, okay, so we are looking into this equation. So, I 1 theta 1 double dot, the pseudo inertial component, plus K 1 theta 1, okay, here it is equals to 0. Now, some portion is missing out here, okay, we will come back to that. After that we cut out the second part, okay. Second part, again the motion is in theta 2, okay. It means that the pseudo inertial component will act in the other way. So, I 2 theta 2 double dot, okay. And since this is moving in this fashion, so the resistance due to K 3 will be K 3 theta 2, okay. So, I 2 theta 2 double dot plus K 3 theta 2, okay. So, there is something out here also, okay. Now, this something. So, the total motion seen by this system is nothing but theta 1 minus theta 2, okay, and it is opposing the motion, okay. So, this becomes K 2 theta 1 minus theta 2. So, this becomes K 2 theta 1 minus theta 2, okay. So, this is the same equation that we have written out here, and the opposing part will be out here, okay. So, this is the, in the similar fashion we have done the same thing for the translation motion, and we are following the same nomenclature, same procedure to write down the equation of motion for a rotational body. Earlier it was a translational body, now the body is rotating, okay. So, same way we draw the free body diagram. From the free body diagram we labeled different components due to the inertia, the stiffness, we wrote down the equation of motion, and from the equation of motion we wrote down it into a matrix formulation, okay. Same principles we are following, okay, and the same analogy we are using what we have learnt in the translation motion, okay. So, we come down to the equation of motion in the matrix form like this, okay. So, from here now we will put some numbers and try to calculate the frequencies and the mode shifts of this system. Okay. So, we are taking a similar system. So, in this example we are asked to find the natural frequencies and mode shifts for the torsional systems. Okay. So, the rotational inertial component I1 or J1, interchangeably we denote by I or J. Okay. So, this is nothing but the rotational inertial component. Okay. So, we are using mass when we are dealing with the translation motion, we are using I or J when we are dealing with the rotational part. Okay. So, here the value of J1 is J, J2 is twice J, and the value of rotational stiffness is same, KT1 and KT2 are same. Okay. So, there are two springs out here. Okay. So, again what we did was we broke down this system, okay, and we broke down this system, okay, and we are writing the equation of we are trying to do the free body diagram of this particular system. So, we are assuming that this is rotating this way. So, the pseudo inertial rotational inertial component will act this way. So, J1 theta 1 double dot, okay, and this is the stiffness component. So, the motion is this way. So, the opposing motion is this way. So, the opposing due to this K1 part will be K1 theta 1, okay. Inertial component K1 theta 1, okay. So, this component is out there, okay. We take the second body, okay, again this is moving rotating in this fashion. Pseudo inertial component will act in the other direction, okay. So, J2 theta 2 double dot. So, J2 theta 2 double dot, okay. Now, for this spring K2, okay, what is the motion that this guy is going to see? The total motion of the systems will be theta 1 minus theta 2. So, K2 theta 1 minus theta 2, okay. So, this is this component, okay, which is opposing the motion, and the similarly for the other part the opposite thing will be there, okay. So, this is again the same thing, minus of K theta 1 minus theta 2, okay. So, this way we wrote down the differential equations of motion, okay, for this particular system, okay. What we did was we broke down this system, okay, we draw the free body diagram of this systems, we identified the inertial components, we identified the stiffness components, okay, we wrote down their directions, and from their directions we wrote down the equation of motion, okay. We are using the same analogy that we have used when we are doing the translation motion, okay. And after that, in this particular problem, the values of J1 and J2 and K1 and K2 are given, okay. So, we substituted back this thing into the equations, okay. So, now we have the equations of motions for this particular case, okay, for the rotational systems, okay. So, again the forcing function is 0, it means that this is a case of free vibration. The damping component, okay, is also 0, there is no damping component in the system is 0. So, this is a case of an undamped system, and since the system is rotating, so this thing we are calling it as a torsional system, okay. So, earlier it was the translation systems, okay, and now this is a torsional system, okay. So, the free vibration of the undamped torsional system, and we are using the same analogy that we have used for the linear movement of the system, okay. So, we got the equation of motion for this particular case. Again, remember for x, okay, for each degrees of freedom, we were saying that the motion of the degrees of freedom is a summation of all the individual components multiplied by a coefficient, okay, a time dependent coefficient, okay. So, each mode is going to contribute, okay. So, the total motion will be contribution from the each mode multiplied by a time dependent component, okay. So, again we are using the same analogy, we are saying that the total motion will be contribution from all the individual frequencies times a time dependent component, okay. So, the same analogy remains here also, okay. So, earlier it was translation, now it has become rotation, okay, where I equals to 1, 2 and 3, okay. So, solving these things we get the frequency equations, okay. So, what we are doing is that from using the same analogy, we are substituting the theta as A1, sin omega t. Okay. We are substituting this in these two parent equations. Okay. So, we are substituting the value of theta I and we are substituting the value of theta double differential I in equation number 1. Okay. So, substituting 2 in 1, okay, we make the similar to this, okay, similar to what we did earlier, okay, similar to what we are doing earlier. Okay. We are in the translation form, we were assuming that x is a function of a time dependent component and a shape dependent component. The shape was given by a sine function. We calculated, we assumed x and then we calculated x double dot. We substituted this back into the parent equation. Okay. In the parent equation, we broke down this thing in this particular fashion. Since a1 and a2 cannot be 0, otherwise there will be no motion in the system, we say that the determinant of this system, determinant of this part is 0. Okay. And then we put down the individual numbers and we wrote down the equation for the determinant, and from the equation from the determinant we wrote down the equation and we changed this thing back into a quadratic equation. Okay. So, the same analogy we are using here for the torsional system also. We are substituting the value of theta and theta double dot in this particular equation. Okay. After that, we will get a matrix of k and omega, okay, multiplied by theta, since, okay, and then we will substitute back. So, we will get the values of ai. So, there will be a1, a2. Since a1 and a2 cannot be 0, otherwise there will be no motion in the system. So, we will say that the values of this part, the determinant of this part is 0 for the non-trivial solution. Okay. And when we evaluate the determinant of this system, okay, 1 multiplied by 2 minus 3 cross 4. Okay. So, when we do the multiplication for these components, we will get a equation, okay, in terms of omega, j and k. Okay. Basically what is happening is there, similar to the translation things, we are getting an equation in omega, and if we substitute omega square as x, okay, so we will get a quadratic equation. Okay. And after that, when we solve for x, x equals to minus b plus minus b square minus 4ac twice a, like before, we will get the solution for our omega. Okay. So, we get the 2 frequency. Okay. So, now earlier it was translation frequency, now this is the rotational frequencies. Okay. So, we get the 2 values of the rotational frequencies. Okay. So, earlier the system was trying to move up and down, okay, because this was the chosen degree of freedom. Now, in this particular case, the system will try to rotate. Okay. So, this will be a rotational frequencies. Okay. So, earlier the frequencies were translation frequencies, now these are, they corresponds to the rotational frequencies. Okay. Putting the values of omega 1 in, after that what we do is that we put the value of omega 1 in this particular equation and we calculate the value of R1 and R2. Okay. So, this way we can calculate the true frequency of the system and the mode shape of the system. Okay. So, what I will encourage here is that you substitute the values of omega 1, you substitute the values of omega 1 and omega 2, okay, and calculate the values of R1 and R2 and plot out the mode shape of this particular system. Okay. So, this is my given system. Okay. Okay. So, try to plot out the mode shapes, okay, corresponding to mode 1 and mode 2 of the system, okay, and see whether this agrees. So, earlier we were plotting out the translation modes, now we will try to plot out the torsional modes. Okay. So, now the modes will be the twisting modes, okay, and see whether the values, okay, or the mode shape that we are obtaining agree to our pre-existing notions. Okay. So, this way we can check and verify our solutions. Okay. So, I will stop here. So, today what we did was we did one more example for the translational case, and then we extended the analogy for a torsional case. We did one example here and we calculated the frequencies and the amplitude ratios, and I would encourage you to plot the mode shapes and check with the existing solutions. Do practice. Thank you.